Hi everybody, and welcome to the video on section 10.3. This video is about compound interest in contrast to simple interest, which we studied in section 10.2, and also APY. APY stands for annual percentage yield, and that is in contrast to annual percentage rate. So the interest rates that are handed to you in a given problem are APRs. The APY allows you to sort of normalize out compounding periods. So that doesn't really make sense right now, but basically when you have compound interest, you can compound, say, monthly or daily or quarterly, and it can become hard to compare different investments that have different compounding periods, and the APY allows you to cut through that and just compare apples to apples. So as I say, that doesn't really make sense right now, but it will make sense by the time we get to it. So these are the two concepts of the video. Before I define compound interest for you, let me just start with an example that compares and contrasts compound interest to simple interest. So consider this example. This guy buys a 2-year, $500 corporate bond. It pays 2% APR simple interest every 6 months. Okay, so what does that mean? That means that after 6 months, the interest is calculated using the PRT formula. So notice this is principal here, this $500, and then the interest rate, and then the time in years. So $500 at 2% interest for 6 months, and again, you have to convert to years, so 6 over 12, that's $5. So after 6 months, he's earned $5. Now, after 12 months, the fact that you've earned this $5 is irrelevant. You use the exact same number here for principal. So you do PRT again, where P is still $500, and your interest is still $5. So after 12 months, the total amount of money you've earned is $10. Okay, I don't know why this is doing this, but let's just ignore it. So here, after 18 months and 24 months, it's the same idea. The principal is $500, so that's what's used to calculate the interest. So in other words, down here at 18 and 24 months, you've earned 15 or 10 bucks or whatever the time period is here. That doesn't matter when you calculate interest. When you're dealing with simple interest, the only thing that matters is how much money you ponied up at the beginning, the initial amount of principal. Okay. In contrast, let's look at an example of compound interest. So here, it's the same setup. We're going to pay interest every 6 months, but now the interest will be compounded. So what does that mean? Well, at the beginning, it doesn't mean anything different. We still invested $500, 2% APR, half a year is $5 in interest. So after 6 months, he's earned $5. Now, though, notice at 12 months, we remember that we've earned that $5. So up here we didn't. We just used 500 again. But now the principal amount has gone up to 505. So now when we calculate interest, we do 505 times 2% times 6 months is now $5.05. So we've earned an extra 5 cents now. And now the total amount of money we've earned over the 12 months is 1005. And since now we've earned an additional 1005, when we calculate interest again, now the principal amount is 510.05, and that's at 2% interest for 6 months, which gives us $5.10. Therefore, the total amount of money after 18 months is 15.15, and so on. So with simple interest, we earned $20 in interest. With compound interest, we earned an extra 30 cents. So you earn more money when the interest is compounded. But this is the fundamental difference between simple interest and compound interest. With simple interest, every time you calculate interest, you just have the same number for principal, $500, 500, 500, 500. But with compound interest, every time you calculate interest, you update that principal amount because you remember how much money you've earned in interest. So that ups the total amount of interest you get. Okay, so that's the difference between simple and compound interest. Okay, now let's be more formal about things. Under simple interest, the gains on an investment are constant. Only the principal generates interest. So notice that was the case in this. The gains from interest were the same every time because this $500 was not changing. So $5, $5, $5, $5. By contrast, when I used compound interest, the amount of interest I got every time was not constant. It changed over time, and in particular, it increased because these principal amounts here were increasing as I accrued interest. So that's all that's saying right there. The amount of interest that you get under simple interest is constant. Oops. There we go. Okay. Under compound interest, not only does the original principal generate interest, but so does the previously accumulated interest. You remember how much interest you have earned, and that prior interest will now generate more interest for you. So compound interest works in your favor if this is your investment. Okay, simple interest works less in your favor because your previous interest is not generating more interest for you. All other things being equal, money invested under compound interest grows a lot faster than money invested under simple interest, and this difference gets magnified over time. If you are investing for the long haul, you should of course always look for compound interest. With compound interest, your previous interest will generate more interest for you, which will in turn generate more interest for you, you see. Imagine that you have just discovered the following bit of startling news. On the day you were born, your Uncle Nick deposited $5,000 in your name in a trust fund that has an APR of 6%. One of the provisions of this fund was that you could not have the money until you were 18. You are now 18 years, 10 months old, and you wonder, how much money is in this fund now? How much money would be there if I waited until I turned 19? What if you wait till you're 60? All sorts of questions like this. So here is an abbreviated timeline of the money in your trust fund starting with the day you were born. The day you're born, your uncle deposits $5,000 in this fund. First birthday, you get 6% interest, and that's added to the account. So here's $5,000 times this 1.06. So what it's doing is it's doing $5,000 plus 6% of $5,000. You see that? So this 1.06 you can think of as 1 plus 0.06. So this is coming from section 10.1 right here. So this number now is the amount of money in your account after 1 year. You have your $5,000 already, and then you have $5,000 plus an additional 6%. Since we're dealing with years here, there's also an implied time unit of 1, but you don't need to slap a 1 on there. For your second birthday, 6% is added to the previous balance, which is now in red. So the balance in the account is now this number. So 1.06 times $5,000, that takes into account that interest you got after the first birthday. And after your third birthday, 6% interest gets added again. And so basically all you're doing is you're tacking on 1.06 times the previous one, which results in 1.06 to the power of your birthday. So notice on your second birthday, you have 1.06 to the second. On your third birthday, you have 1.06 to the third. So as it says down here, you might have noticed that the exponent of 1.06 goes up by 1 on each birthday, and in fact matches the birthday, and that is correct. So on your 18th birthday, the balance in the account is 1.06 to the 18th times $5,000, and you can just have a calculator verify this for you. 1.06 to the 18th times $5,000 is just over 14,000. So not bad. Since the bank only credits interest to your account once a year and you haven't turned 19 yet, the balance in the account is still that. So let's see what happens if we wait till we turn 19. The future value is now, we'll just replace that 18 with a 19, and you get just over 15,000. So if you're willing to wait 2 months, you will essentially get $900, $1,000 in extra money. What if you wait till you're 60? The future value is now, we'll just replace that 19 with a 60, and you get just over $160,000. So not bad, right? Your uncle invested $5,000 for you, and that $5,000, what happened? It increased by a factor of, what? I'm bad at math in my head, but you can multiply this by 30, and get something close to this. So by a factor of 30, a lot. Okay, so this graph here shows you the amount of money in years. So it's increasing, of course, and it actually will start curving up. So if you let this graph go even farther to the right, the rate of growth just keeps going up and up and up. So this is not a straight line. It's actually better than a straight line. So a straight line would sort of angle like this, and it would be underneath these red dots. These red dots are growing exponentially, actually. They're growing quite fast if you zoom out, as this figure does, right? This is now zoomed out. Over the 60 years, notice the red dots like start shooting up. Right? So this is not linear growth or something. This is exponential growth here. The future value of P dollars compounded annually for T years at an APR of R% is given by this formula here. And just to be clear here, when it says compounded annually, what they really mean is you calculate interest at the end of each year. So the time between each interest payment is 1 year. That's what it was in this example here, right? Every year we calculated interest, but no more often than that. So the future value of the money is the principal amount times 1 plus the APR in decimal raised to the T power. That's exactly what we saw in the previous example. Let's move on to a different example. Imagine you have $875 in savings. You want to invest it. Your goal is to have $2,000 saved in 7.5 years. You want to send your mom on a cruise or something, whatever context you want to give it here. Imagine now that the credit union around the corner offers a certificate of deposit with an APR of 6.75% compounded annually. What is the future value of your $875 in 7.5 years? If you're short of your $2,000, how much more would you need to invest to meet that target? So let's start with the first question. To answer the first question, we apply the annual compounding formula that we just had, right? This guy here, where you're investing $875, right? So that's how much money you have now. So in this formula here, P is $875, R is 0.0675 because you had to convert that 6.75% to a decimal, and time here is the time in years, and that's 7.5. So it actually doesn't matter. You can write 7 or 7.5. With annual compounding, fractions of a year don't count. Okay, so in general, if you do annual compounding, you would round your year amount down. So if you were doing something like monthly compounding, which we will do later, you would keep that 0.5 there. Okay, in any case, what you get is 875 times 1.0675, that's that 1 plus 0.0675, raised to the 7 years, and you get approximately 1,400. So you are quite a bit short of your target. So to determine how much you should start with to reach that target, let's now leave this P blank. Right? So now we don't know the present value that we need to invest, but we know our target future value. So in this case, if we put 2,000 over here and then solve for the principal that would get that for us, using the same formula, we can find out how much we should invest now. So with your calculator, you should ask it what 1.0675 to the 7th is, and then scoot that over, just divide it over, and you end up with a principal amount of 1266.06. So, that's quite a bit more than you wanted to invest right now. So let's now return to our story from the previous example. $875 you have to invest, 7.5-year window in which to invest your money. As we discussed in the previous example, the 6.75% APR compounded annually doesn't get you where you want to go. And by the way, if you can find a certificate of deposit that would pay you 6.75%, please let me know. This is like 10 times larger than you'll find right now in the current market. This is extremely good right now. Nobody will pay you this. Okay, but anyway, we'll take the number as just a part of this toy example. Now imagine you find another bank that's advertising 6.75% APR that is compounded monthly, not annually. So what that means is now they calculate each interest each month rather than each year. So inside of a single year, they're calculating interest for you 12 times, not just one time. It seems reasonable to expect that monthly compounding could make a difference and make this a better investment. Why is that? Well, because if you only compute interest at the end of the year, now you have the interest there that will generate future interest for you. But imagine you computed interest at the end of the first month. Now that bit of money will grow over the next 11 months. And same thing for the money you get after 2 months. That will grow for the next 10 months, etc. So if you compound monthly, you get a bunch of extra little interest payments that grow for you throughout the year that you did not get when you compounded annually. To do the computation, we can't use the annual compounding formula because it's an annual compounding formula, right? Annual. So since the interest is compounded 12 times a year, the monthly interest rate is now gotten by taking the original APR, which is an annual number, and dividing it by 12, because there are 12 months in a year. So the interest per month is 0.5625%. Okay, so pretty small. So here's an abbreviated chronology of how your money grows. You start with $875. Month 1, that 0.5625% interest is added to the account, so the balance is now this. And then, just like before, we do the same thing. Well, after 2 months, you now have 2 of these guys. 3 months, you have 3 of these guys, etc. So after month 12, you have $935. After 7.5 years, which is 90 months, you now have $1,450, which again is far short of your $2,000 goal, but it's actually more than you got with annual compounding. So what did we get with annual? We got where was it? $1,382.24. That's how much we got with annual compounding. So with monthly compounding, we got an extra $60 out of it. So it's not giving us as much as we want, but it's closer to our goal. So imagine you find a bank that pays a 6.7% APR, but is compounded daily. So what does that mean? That means they calculate interest for you every day. Not every month, not once a year. So that sounds good to you, right? The more often you compound, now at the end of day 1, you're going to get some interest that will grow over the next 364 days up until the end of the year, right? And then keep growing beyond that. But the more often they pay you interest, the longer that little bit of interest has to grow for you. So daily should be better than monthly. So the analysis is the same as the previous example, but now we compound 365 times a year, excluding leap years, and the numbers aren't quite as nice. Now we have a daily interest rate, so take the annual one and chop it into 365 parts, and you get this 0.000189, so it's very small. Next, we compute the number of days and the 7.5-year life of the investment. Well, 365 days in a year for 7.5 years is 2,737.5 days. So since half days don't count, just like half years didn't count for annual compounding, we round down. So the future value is take 1 plus your daily interest rate, raise it to the number of days, times 875, and you get 1451.47. So that didn't do a whole lot for us over the monthly compounding. So monthly was 1449, right? This is now 1451. So daily compounding only got us an extra $2. So let's summarize all this. Each of these examples gave us a scenario in which the present value was the same, and the APR was the same, and the length of the investment was the same. The difference was how often we compounded the interest. Annual compounding got us a future value of 1382.24, and here are the other 2 numbers. Right? So notice the more times you compound, the higher these numbers get. Notice also, though, that it's not like the numbers just keep shooting up indefinitely. Right? There certainly seems to be a cap on how much money we're going to get here. So if we compounded every second as opposed to every day, we're not going to get magically 20 grand out of this. You know, we're probably going to get something close to this 1451 number, maybe slightly higher. A reasonable conclusion from these numbers is that increasing the frequency of compounding is not going to increase the ending balance by very much once you get down to things like seconds or nanoseconds, right? Going from yearly to daily did make a difference, but beyond that, it doesn't seem like we're going to get much more money out of this. So the future value of P dollars in T years at an APR of R% compounded N times per year. So think monthly, right? The formula is this: the amount of principal you invest times 1 plus APR in decimal divided by number of times you compound per year, all raised to the exponent NT. Number of times per year times number of years. In the general compounding formula, R divided by N represents the periodic interest rate, just like we did in the example, and it expresses it as a decimal, and the exponent N times T represents the total number of compounding periods over the life of the investment. So, imagine you compound monthly for 2 years. Well, if you compound monthly, N is 12, and T is 2. 12 times 2 is 24. So over 2 years, you will compound 24 times. That's what that NT is telling you. If we use P to denote the periodic interest rate and capital T to denote the total number of times the principal is compounded, then we get something that looks like this. So this formula is saying the exact same thing as the previous formula. It's just that P, little p here, happens to equal R divided by N, and capital T equals little n times little t. So I don't care which formula you think in terms of, it doesn't matter, but they're saying the same thing. One of the remarkable properties of the compounding formula is that as n grows without limit, the future value f approaches some cap value L. So as you compound every second, every nanosecond, every millisecond, whatever, you can't just make your money grow indefinitely. There's some sort of cap on the amount of money you can get, and that cap is called L. So this limiting value represents the future value of an investment under continuous compounding, where continuous compounding, imagine compounding every nanosecond, right? Whatever the shortest length of time the universe can sustain, a nanosecond, whatever, that's how often you're compounding. And in that case, if you compound continuously, the future value is given by this formula. P times the number E. So if you don't know what this number is, you can just think of it as basically 2.718. So that's approximately what it is. And you take that number E and raise it to R times T. So that's the best you can do. Compounding continuously is the best you can hope for, because that means you're compounding every possible time you can compound. So you find a bank, offers an APR of 6.75%, and they compound it all the time. Using the previous formula, we get this future value. So we do 875 times the number E raised to the exponent 7.5 times 0.0675, and we end up with this number in the end here, 1451.68. So if you invest $875, this number here is the best you can hope for at an APR of 6.75%. So of course, if you find a bank that gives you a higher interest rate, or you are willing to let the money sit longer, then yeah, you can up this number. But given those two constraints, your $875 will turn into 1451.68 at the best. So your target was $2 grand. You cannot get $2 grand out of your $875, again, unless you're willing to find a higher APR somewhere. So when you compare the future value with the future value under daily compounding, notice we haven't increased very much. So this 1451.68 is only 21 cents higher than we got with daily compounding. So once you're willing to compound daily, compounding more often than that won't get you very much more money. Okay, so the big takeaway from this section on compound interest is this formula, which you can think of as this formula if you want to, and also this formula. So these are the compounding interest formulas. If you compound all the time, always, compounding continuously, this is the formula you care about. If you compound a certain number of times per year, then this is the formula you care about. Now, let us move on to APY. The annual percentage yield of an investment, sometimes called the effective rate, but more often called the APY, is the percentage of profit that the investment generates in a one-year period. So, suppose you invest $1,000. After 1 year, you have $1,099.60. You made a profit of $99.60. So, what percentage of 1,000 is $99.60? Well, $99.60 is 9.96% of 1,000. And 9.96% is my APY. So that's what APY means. Take whatever your profit was, ask yourself, what percentage of my original investment was this profit? And that's your APY. So after a one-year term. Suppose you invest $835.25. At the end of a year, your money has grown to $932.80. So, yeah, the details of how your money got that way are totally irrelevant for now. So how do you compute the APY? Well, the APY was, look, 932.8 minus 835.25. What does that represent? That represents the amount of money you made. Right? So you moved from 835 to 932. So to figure out your profit, you just subtract the two numbers. And then you divide by the amount of your original investment. That gives you a number of 11.68%. So this is how you can always calculate an APY given a one-year growth. So if I tell you, here's how much you made, here's how much you invested, here's how much you have at the end of a year, you can always just take your profit divided by the original investment, and that will tell you your APY. Yeah, so in general, if you start with S dollars at the beginning of the year and your investment grows to E dollars, the APY is the fraction E minus S, which represents your profit, divided by the size of the original investment. And this we've already seen in section 10.1. In some sense, it's the annual percentage increase of your investment. So here is the main way that APY is useful. It's used to compare different investments. Here are three different investments with three different APRs. 6.7% compounded continuously, 6.75% compounded monthly, or 6.8% compounded quarterly. And quarterly means 4 times a year. So these are investments, right? And with an investment, you want a high interest rate. The higher the interest rate, the more money you will make off of your investment. So without doing anything, we might speculate that answer C is what we want, because answer C has the highest interest rate. So we'll investigate that. We'll see if C is the best. Before we do that, though, notice that this question is independent of the principal and the length of the investment. Okay, you don't need to know those things to compare these investment opportunities using the APY. Okay, so let's compute the APY. The future value of $1 in 1 year at 6.7% interest compounded continuously by our previous formula is given by this. E raised to the interest rate, which is 1.06930. So notice that the profit I got was 0.06930. If I divide that by my original investment, I get 0.06930. So in this case, the APY is 6.93%. So you can see here the reason we used $1 as the principal is that, come back up here, right, when we do this calculation, profit divided by original investment, if your original investment was $1, dividing by 1 is simple. Okay, let's look at scenario B. The future value of $1 in 1 year at 6.75% interest compounded monthly. We now use the compounding formula and we get 1 plus the periodic interest rate. So 0.0675 gets divided by 12, raised to the 12 because we're compounding monthly, and we get 6963. So in this case, the APY is 6.963%. So notice that that is better than this, right? 6.93 plus a little extra, or sorry, 6.96 is better than 6.93. Okay, so now let's move on to the, oh, sorry, this is just a typo. This should be a C, right? So the future value of $1 in 1 year at 6.8% interest compounded quarterly is again given by the general compounding formula, and here's what you get, 1.06975. So the APY in this case is 6.975%. So although they are still quite close, we can now see for sure that C is the best choice, B is the second best, and A is the worst choice. So this is what we suspected to begin with, but it is very easy to come up with examples where you get something you don't expect. And the idea of this example is that computing the APY cuts through these different compounding periods. So A is compounded continuously, B is compounded monthly, C is compounded quarterly. How do you compare these things? You know, the way you compare is by computing an APY. So once we calculated the APYs, we saw that C's was the highest, B's was the second highest, and A's was the lowest. So although the differences between the three investments may appear insignificant, these differences become quite significant if you're going to invest over like a 20 or 30 year span. Okay, so that is all I have to say about section, about section 10.3. The main takeaways from this are the definition of APY, the definition of compound interest, and the compound interest formulas. So as always, if you have questions on anything, please contact me.